let me take just a minute to also dissect this a little bit as well, to give you a way to understand this very complex formula a little bit more. I'm sure Chris did a very good job in explaining the proper derivation of it. But just to give you a quick version of it, well, let's start with that. It's from Fourier series. So we talk about Fourier series. It's basically a little bit like Taylor series, but it works for periodic functions, right? Now, here's the tricky bit: is what if we extend that period to infinity? Now, you might then it sounds like, well, it's no longer periodic. I might as well do a Taylor expansion. But it has different uses, because Taylor series is using polynomials, well, x0, x1, x squared, as a basis. Okay. And for Fourier series, this is Taylor series. For Fourier series, you're using sines and cosines of different well, this was nx, but more precisely n pi x over L, right, as the basis. So instead of xn in general, you're using different sines and cosines. So if you know that you're modeling some sort of wave, even though the wave is not necessarily strictly periodic, or the period is very large, this would be a better way to expand it, and it captures much more of the essence of it. And for example, if you have a partial differential equation, you set a boundary condition. We talk a lot about boundary conditions in this module. You fix the two ends. You know there's some sort of oscillation going on. This is a much better way. Okay, so Fourier transform is taking that and stretching this to infinity, right? So you're using these bases and stretching that out. So the idea from Fourier series is you can write this. I won't write out the whole thing, but sine pi x over L, sine of the same thing, right? And you know that there's a subsection in your notes that show you, because cosine and sine is basically, you can group it in here. You can combine that into a complex representation like this. Okay, so you can expand that out and see how does AN and BN relate to CN. It looks a little bit interesting at first that suddenly you have two independent coefficients. Suddenly, how come you have one? But you remember, this is now complex. So there's actually a real part and an imaginary part. So actually, there's 2 degrees of freedom over here. So yeah, there's 2 things that actually correspond to there. So if you take the real part, roughly speaking, corresponds to the A, like that. A little bit more subtle, but you can check, right? And also a second thing is, now this has the power of extending it from 1 to infinity to minus infinity to infinity, because the only reason why this starts from 1 or 0 is because these are nicely even and odd functions, but here now it groups nicely into this compact form. Okay, so this is sort of most mathematicians kind of like this better. Instead of writing cosines and sine, it's more compact. Now, if you extend L out, you now want to see if I can make this a continuous function. Instead of writing C, instead of writing Cn, let's write that C as a function of K. Okay, so instead of n going from there, from minus infinity, you start from K going from minus infinity to K going to infinity, right? And then you still have here. So roughly speaking, again, this is a rough derivation, not the proper one. You can look back at the notes, but just to give you a better idea, right? So n, roughly speaking, is K. Okay, so I have factors of pi's and l's not properly derived over here, but just to get you the idea, right? So, so you can think of ck dk as basically the coefficient over on here. So you're taking a function and expanding it out like that. And of course, instead of ck, we're going to call it f of k. So it's ck, we're going to hat of k like this, right? So you can see it's basically a continuous version of it, and I won't prove the inverse. You you can invert it and flip it back over here. Another point to, another tip is how to remember where does the 2 pi go. That's actually a slightly matter of convention. Mathematicians actually put the, 1 over square root of 2 pi on each, so you don't have to remember why does one doesn't have a 1 over 2 pi and why does the other have a 2 pi. But for physical purpose, for most of physics and most science, k represents either frequency or wavelength, okay, or wave number, and the k over 2 pi has a very good physical representation. So I'll leave the application more to later. But yeah, so the idea is to always remember sort of k over 2 pi kind of goes together, okay? You can kind of think of it like relationship in wave theories, right? So the k and the 2 pi sort of goes together, yeah, and the dx sort of goes alone. So whenever you see a dk, it always comes with a 1 over 2 pi.